if you recall, we want to start describing functions of two variables. We need to move from R2 up to R3. And we're going to need to describe how to picture things in R3. The first stop on this trip is to describe graphs of functions. We know that the graph of a function of one variable is a one-dimensional curve in R2. The graph of a function of two variables will produce a two-dimensional surface in R3. Our job is to describe those surfaces, actually try to picture those surfaces when we can. We can't always do this, and we shouldn't rely on having to think of a picture of what we're trying to represent. At a certain point, we lose the ability to actually create a picture in our mind of what's going on, because we'll have a function of three variables. It's sitting in R4, and we're not programmed to envision things in R4. We're going to have to find a workaround for doing that. The workaround for doing that is picturing slices of that thing in 4 dimensions by looking at 3-dimensional slices. To do that, you have to understand what surfaces look like in R3. So that's our goal. Last week, we looked at an example where there was an x squared plus y squared. When we see x squared plus y squared, we know that we're going to be seeing circular slices. We're going to see some level curves that are going to be circles. Today, we want to look at a little bit about how things are changing. The other thing that came up last week, I'm trying to think about why I wanted to do this. Oh, I remember, it's the quiz. Last week, from the top, our circular paraboloid looked like circles, and then from the side, we saw parabolas. So we want to recognize some other shapes. In the quiz that we had over the weekend, we had a function of x and y, and we didn't have an equation to look at. We just had patterns in numbers to look at. So we want to identify some rates of change that we should be able to recognize in numbers. All right, let's talk about some rates of change. So our favorite one is the default setting for thinking about how things are changing. Linear functions. Our default setting is linear functions with a constant rate of change. Linear functions with their constant rate of change have a predictable pattern. I like to describe a linear function as having a pattern of repeated addition. Linear functions have a pattern of repeated addition. Now, I know we're all familiar with linear functions, but let's talk about this pattern of repeated addition that I like to identify. Let's talk about how we use this to describe the rate of change. We're going to go with the function of just one variable. So for example, if we have the linear function y is equal to b plus mx. I know we're all conditioned to write this as mx plus b. That's terrible. We should write it in this direction, b plus mx. It's more descriptive of what's going on, and this is how we write exponential functions, which are very closely related to linear functions from a structural standpoint. What this equation is telling you to do is to start the y values at b and then add m a bunch of times. That is just what this says. We're just taking that description and encoding it in an equation. So this says y is b when x is 0. So we're saying start at b and then add m a bunch of times. The next thing after the b is plus m. It's telling you to plus m. Oh, this is the red. This is the repeated addition of what happened. This is the thing. Y increases by m every unit. And because it's m, and we're multiplying by x, we're saying a bunch of times. Start at b and add m a bunch of times. Repeated addition is summarized with multiplication, and that's why we describe our linear functions with the multiplication. We're adding m a bunch of times. If we're adding the same thing a bunch of times, we use multiplication to represent repeated addition. This is nice. It goes back to the basis of everything, addition. That's the first thing that we have to learn about with number, addition. Your whole arithmetic class was about doing addition and all the fancy ways that we can do addition. Now, this is the form where it says start at b and add m every 1 unit, but we know that the slope is usually a summary of rise over run. So a lot of times instead, we'll see something like y is equal to b, add the rise every run unit. I know that this is not how we normally write linear functions. It would be weird if you started writing linear functions this way, but this is how we can think linear functions. Start with b. Add the rise every run units. Start with b, add the rise every run unit. Now, because the rise is just being multiplied by x over run is the number of times we've added the rise. Because this is multiplication and x divided by the run is division, we can commute these two. We can just take the rise, divide by the run, and then multiply by the x. Or you can take x divided by the run, then multiply by the rise. Or if you can also, I guess, multiply the rise by x and then divide by the run like a damn sociopath. But it's just all mixed up because it's multiplication, division, doesn't care what order we go in. Normally, we don't write it this way. We put the run under the rise and summarize. And then when we get to exponential functions, we can't make them anymore, even though it has the same structure. We're just trading out our multiplication for our addition for multiplication. So annoying, but so be it. Linear functions have a constant rate of change. We're well versed in this. We know what it should look like. So if, for example, we've got a linear equation, y is equal to 10 minus 4/3 x. We could say, let's start y at 10 and subtract 4/3 every unit. Or we could start at 10 and subtract 4 every 3 units. So we could read this as start off at 10 when x equals 0 and subtract 4 every 3 units and subtract 4 every 3 units and subtract 4 every 3 units. Or we could start off at 10 and subtract 4/3 every 1 unit. 10 minus, what's 10 and negative 4/3? 8 and how much? Decimals. Why so fraction hating? What's wrong with fractions? Y'all number racists? I wasn't going to do this one. That's why I wrote this one first. But I'm like, oh, no. I've got fractions today. I'm like, oh, clearly I don't. I don't have fractions. Oh, well. 10 and negative 4/3. So 9 and negative 1/3. 8 and 2/3. Is that right? Close enough. And so on. I'll do that one. I'll just get to the one that I know. In case you were wondering, I was just like writing down some stuff. I can't do calculations without writing stuff down. But I'm writing in pen, so I can't erase it and try to hide it. Like what, you know how when you're like doing stuff on paper and you're like, oh, 17 times 3, 17 times 3. And then like off in the corner of your quiz or something like that, you're like, oh, 17 times 3 is 21 and 30, 51. And then you like erase it. But I can still see it. Why did you bother erasing it? Why did you erase it? Did you want, are you trying to hide from me? Oh, I don't want Leach to know that I had to multiply 17 by 3 over here on the side of the paper. Oh, I don't want to. Am I really going to care about that? I'm like, oh, look at all this stuff. Came up with 51. Everything looks great. What's this? Oh my God, did they have to write that down? Minus 10 points. Meanwhile, I'm up here every day. I'm like, well, 17 times 3 is like 60 something. Yeah, 60 negative 9. Got it. So, I mean, just write it down. Just leave it there. Now, it's one thing if your writing is like all super neat and you like turn in like what's like a final draft. And Michael, did I give you 2 copies of the quiz and you wrote a rough draft and then this is the final copy? Like some people like have like stuff that I could frame. I'm like, oh, and my wife will come home and say, oh, what's this on the fridge? I'm like, oh, that's a quiz from a student. Look at that. It's fucking beautiful. You know, she like, all the answers are wrong. It doesn't matter. Look at the writing. Look at the penmanship. Dedication to detail. Do you see where they multiplied 17 by 3? And she's like, oh, no. It's like, oh, because you can't. They erased it properly. Shit. And I come back to class, I lost your quiz. Meanwhile, it's framed, hanging in. I'm just kidding. I would hang it in my office. Anyway, it's cute that you like try to hide this. Like, oh, no, I didn't have to write that down. All right, so, oh no, now I can't erase it. No one can. See, he works for the CIA. No one can. Like in Jurassic Park. So we have this constant rate of change. We are subtracting 4 at regular intervals. -4, -4, -4. There's that constant rate of change. The slope is the constant rate of change per unit, so -4/3. But as long as we have a regular same change over the intervals, linear. We like this because it's our default way of thinking. The default way of thinking is to make linear functions. We just connect point A to point B in a straight line. If we're bargaining and I say I'm at $3,000 and you're at $5,000 and we agree to split the difference, we just land on 4. We make a linear function between our 2 points and we go halfway. We make a linear function. I don't. I make a geometric mean. So I make a geometric mean if I'm at the lower end. Other patterns that we should recognize is one up from this. And that's identifying a quadratic function by its rate of change. A quadratic function will have a linear rate of change. And we know this already because we know that in calculus, rate of change means derivative. The derivative of a quadratic function will be a linear function. Let's identify this in numbers. And let's just use our I'm worried about my ability to do calculations this early in the day, so we'll just go with the easiest quadratic function there is. What we want to notice is how the rate of change is changing. So we don't have a constant rate of change. Rate of change is just how much the function is changing. From 1 to 0, it's a decrease of 1. From 0 to 1, it's an increase of 1. From 1 to 4, it's an increase of 3, and then 5, and then 7. So it's not a constant rate of change. The rate of change is not constant. But if we look at the rate of change of the rate of change, from -1 to 1, the rate of change increased by 2. From 1 to 3, we have a rate of change of increase by 2, and so on. The rate of change of the rate of change is constant. And this still makes sense. This still fits with our interpretation of rate of change as derivative. The derivative of the derivative is constant. That's how we think about quadratic functions and how they're changing. So that shows up here because the first thing that we look at when we are trying to decide what a function looks like and how it's going to be behaving is we look at how the function is changing. If we think about the quiz, in the x direct, we have these numbers. We have 14, 10, 6, 2, and then we have 16, 12, 8, 4. What we see here is that we have in this quiz, we had a constant rate of change in the y direction. We have a constant rate of change in the y direction. So we have 26 minus 4 is 22, minus 4 is 18, minus 4 is 14. So we had a constant rate of change in the y direction. And in the x direction, we went from 14 to 16, from 16 to 20, and then from 20 to 26. Here, the rate of change was not constant. From 14 to 16, we see an increase of 2, and then an increase of 4, and then an increase of 6. So here, our second derivative is linear, so it looks like we have a quadratic in the x direction. We don't have a lot of data to go on. But based on this, it looks like I built this with a quadratic function in the x direction and a linear function in the y direction. Any questions? We want to be able to recognize patterns. What we're trying to do with math, the overarching goal is to describe what's going on. We want to look at patterns and try to quantify those patterns, classify those patterns. The more patterns that we can identify, the better our math is going to be. That's the point. I know y'all think the point of the math, learning about math is not so much to describe the world, but to get a job as an engineer because you heard it pays good. And we're playing a capitalism game, so shit, paying good is good, right? That has to happen. Kind of like if you can do this kind of work, then maybe you should, because it could be beneficial. Not to humanity. I mean, like you could make more money and buy a nicer car than your neighbor. Your neighbor shows up in a Lexus, and then you can show up in a Mercedes. They show up in an E class, you could show up in an S class. They show up in an S class, you get out of the back of the S class when your driver lets you out. That's the whole point. I'm not sure if anybody is here to become wealthy. Don't raise your hand if your goal is to become wealthy, but the best way to become wealthy, I know the secret. The best way to become wealthy, is everybody ready? It's to have wealthy parents. So if you were not born to wealthy parents and you want to be wealthy, you've already fucked it up. Why didn't you pick the wealthy parents? If you're like, oh, I want to be wealthy so I could jet around the world and not have to work. Then you're like become born. It's like, well, why did you pick those parents? They're not wealthy. What did anyway. Anyway, what are we talking about? Oh yeah. I like eventually I'm going to start making fun of engineers, and I know most of you are going to be engineering students, and I'm not I was an engineering student too, so but recognize that when mathematicians start making fun of you because you're an engineer, think about in the apocalypse bunker when there's one seat left, who's going to get it? It's not going to be me. I'm going to show up and say, well, we've got one seat left. We might as well give Leach a spot. I heard he's on a diet, so he's not going to eat as much. I'm like, well, that's true. It's like, I know math. Like, all right, he knows some math. All right, let's get him in here. Then an engineer's like, oh, hey, I'm an electrical engineer. It's like, oh, Leach, you're out. Just like instantly. Like, oh, like circuits and stuff, and you're like, oh, yeah, mostly in computers and shit. But you're like, oh yeah, totally. And then they go, all right, Leach, you're out. Engineer, you're in. And then there's going to be before the door closes, there's going to be a quick knock. It's like, oh, I'm actually an electrician. Then the engineer is right out, and the electrician's like, oh no, this is some guy who's actually rewired a house. So anyway, what are we talking about? That one's especially on my mind because I just had to rewire my house. I just had to have someone rewire my house because fuck that. I'm not going to kill myself to save whatever money it was. Do you know what I mean? I had knob and tube wiring, for those of you familiar with housing wiring. My house is from 1926. This is the original wiring. This is the wiring that they put in 1926. Oh, this will be good enough. There's a lot of exposed wire. Yeah, it's behind the wall, so we'll be fine. Great. Then fast forward almost 100 years. You're using how much electricity? It's like, oh, I've got to run the internet. The inter what now? And so the last time we had to do a repair, the repair guy's like, oh, you might want to address this wiring. I'm like, oh, why? We don't do this anymore. It's like, oh, why? Because it sets houses on fire. I'm like, oh, fuck, I'll call the electrician. And the electrician's like, oh, not only am I going to have to rewire your house, I'm going to take your spot in the bunk. I'm like, oh, shut up. I know. At least the check is going to clear, right? One other one that we should just recognize in the numbers. Remember, we want to recognize things in their form, their algebraic form, and their numeric form. That's what this quiz was about. I wanted to put out something that was linear in one way and quadratic in the other. The other one that we want to recognize is exponential functions. I like to describe exponential functions as having a proportional rate of change. That is, if we double the value of the function, the rate of change will also double. That's proportional. If we cut the value of the function in half, the rate of change will also be cut in half. The way that this shows up is we have a pattern of repeated multiplication. Exponential functions with their proportional rates of change will produce a pattern of repeated multiplication. The other way to identify an exponential function is that the increase will be by a percent. This is equivalent to saying proportional rate of change. The amount of change is some fraction or percent of the amount of function. Structurally, we could set these up very similarly to linear functions. Start off at 10 and multiply by 2 every 3 units. Y is 10 when x equals 0. And we're going to multiply by 2 every 3 units. Y is 10 when x is 0, and y is multiplied by 2 every 3 units. This is a pattern of repeated multiplication. If we want to construct a table of values, in 3 units, we multiply by 2. We multiply by 2 every 3 units. We multiply by 2 every 3 units. We multiply by 2 every 3 units. That's the pattern that we see in an exponential function, a pattern of repeated multiplication. And it's set up the same that we did with a linear function. But instead of adding the rise every run units, we're multiplying by some multiplier every run units. So we're multiplying by 2. This is how we're tracking the chain. When we want to think about rate of change, we still think about what we're adding. In thinking about rate of change, we still think about how much we add. From 10 to 20, we add 10. Then we add 20. Then we add 40. Then we add 80. So the rate of change is proportional to the function. When the function was twice as big, the rate of change was twice as much. When the function was doubled, the rate of change also doubled. The rate of change is proportional to the function. This shows up mechanically as what we call multiplication. That's our pattern of repeated multiplication. So we build these exponential functions because the variable shows up as an exponent because we're doing repeated multiplication, and exponents are repeated multiplication. We want to do this because we want to be able to recognize when we see a known pattern in numbers. We want to recognize known functions in their algebraic form and also their numeric form. And we want to be able to describe what those functions are. So this was not so much of a Calc 3 thing today, except if I take two of these and just kind of put them in the two different directions. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.